Just for fun, try and solve the Helmholtz equation in free space in cylindrical coordinates and look at the solution that you obtain and see if you notice anything peculiar. Pause the video and see what happens. This is basically a straightforward extension to the calculation of the modes in an optical fiber, because there in the core, if you take the core and you extend the radius towards infinity, you basically end up with free space again, right? So you can follow exactly the same line of reasoning to come to the conclusion that the field in free space will be proportional to a Bessel function of a certain order L, and then a radial transverse wave vector here, and then exponential minus JL theta for the angular dependence, and exponential minus j kzz for the transverse dependence. Again, there could be a second solution, not with j's but with y's, but we discard that solution because in the origin that solution would blow up otherwise, and that's not physically plausible. So this is what we have. If we now look at the intensity, so the modulus squared of this thing, you will basically realize that everything related to the theta dependence and the zeta dependence drops out. So it's going to be something which in its transverse profile does not depend on the propagation direction, on the z direction. So it's very similar to what you have in a waveguide, something which does not change as you propagate in a certain direction. So in essence, what you have is a non-diffracting beam, and this non-diffracting beam is called, unsurprisingly, a Bessel beam.